Welcome to ICDD's InSession webinars and Dr. Partha Das's presentation, Unlocking the Past, Electron Diffraction for Ancient Material Characterization. Please remember to visit icdd.com for information on free webinars, educational events, PDF databases, and JADE software.
Okay. So first, I would like to sincerely thank ICDD for their kind invitations to be part of this webinar series. And a big thank to the ICDD team to make everything as smooth as possible. And I would also like to thank all the participants to join this webinar. For some people, it's maybe morning, some people for the afternoon, and some people for the evening, depending on your time zone you are joining. I am all glad to be all you are here. So for those who are not familiar with Nanomegas, we are a company based in Brussels. We are pioneers in providing advanced solutions for electron diffractions. Our portfolio includes several innovative tools and solutions which is compatible with all major diffraction columns. To date, we have close to 300 installations worldwide based on electron diffraction solutions, and our technologies contributed more than 1,000 publications in last 25 years. And we are actively participating in many European projects, including some of them we have coordinated. If you'd like to learn more about our technologies, you can visit our websites. Now I'll walk through some of the few examples during our presentation, especially those related to the analysis of ancient materials. Here is a quick overview of all the techniques which is mostly used for the ancient material study. One of them is optical microscopy, which gives a very good inspections of the surfaces and layers. And another one is XRD, which is very widely used. It identifies crystalline phases for pigments, pottery, corrosion layers, and it has been used extensively. But the challenges comes in when the sample quantity is very small or there is a mixture of phases. The another technique which is used extensively in ancient material characterizations is the ACM with the EDX, which gives very high resolutions images with elemental compositions, but there are challenges like sample coating and when the sample is non-conductive. Portable XRF is used also extensively in the ancient material characterizations. It's very fast, non-destructive, but the problem is it does not give much of the structural data. Raman and FTI are also used extensively in ancient material characterizations. It is used in dyes, binders characterizations, but signals become weak as soon as it used in degraded materials. And finally, depending on the case studies, you can use other techniques like synchrotron-based techniques. There are isotope analysis, all depending on the particular research questions what you are looking for your analysis. I would suggest combining all these techniques is very useful when you are analyzing a complex materials. Among all these techniques, transmission electron microscopy stands out as one of the very powerful techniques which has not been extensively used for ancient materials. It's like an optical microscope, but we have a very short wavelength of the source, and it gives many things at the same time. If you have not seen an electron microscope before, or you have not used it before, it looks like this in the middle, as you can see it gives diffractions, imaging, spectroscopy like chemical analysis from a very small quantity of samples. It operates between 100 and 300 kV. As it operates in a very short wavelength, it gives a nanometer scale resolutions. All you have heard about the dynamical diffractions from electron diffractions, but there are ways to reduce it, like using beam precessions, which Nanomegas is a pioneer of. But I'm not going into the details of the techniques here, but I will show you how it can be used to characterize ancient materials. There are different ways of doing sample preparations for TM. One can be done by very simple way, just by you place a small quantity of powder on your TM grid and you do your study. But sometimes that is not possible, to crushing the sample. In that case, you can do very advanced sample preparations like FIB to take the part of your interest. I'll show some example where we have used this special focused ion beam technique to prepare samples from ancient materials. Most of you are familiar with diffraction itself, so I'm not going into the details what diffraction is, when diffraction happens, the Bragg's law and everything. Let's see in real life examples. These are some of the examples I have taken from a review from Philip Seo. He has done some excellent work using imaging and diffractions. The first example comes from a materials which is a transparent glaze, and it gives an amorphous diffraction patterns. And this confirms the materials is amorphous. And then it could be a materials like the example number 2, where it gives a polycrystalline diffraction patterns. In that case, you can do some radial integrations, and then you can do phase analysis using ICDD database, combining EDXS to help you to pinpoint the mixture of phases present in this sample. And if you are lucky, then you get a single crystal pattern for a sample which you have seen it here in the third one. Then you can just go and straight directly to the ICDD database, index it, and combine with your EDX to pinpoint the phase of interest. All this is nice, but what happens when the phase is absolutely unknown? In that case, the technique which is used, and I will go through it a bit briefly, is called 3D electron diffractions, which is quite popular these days. Some people call it micro-ED techniques. Though this technique was developed something like more than 15 years ago to solve many structures of inorganic materials, now it's becoming more and more popular, where you just find one crystals in your TM grid, then you tilt the crystals by stepwise or rotate it very fast and collect diffraction data during this tilting of the crystals. And as soon as you have a crystals diffraction data from your three-dimensional diffraction data, then you treat it as like a diffractions coming from a single crystal sample. And once you have this three-dimensional diffraction data, you just extract intensities, solve structures. I call it single crystal data from a teeny powder diffraction screen. Now I'll go through some of the examples where this technique has been used to solve some nice structures from some corrosion materials. The first examples comes from a sample which I received from a collaborator from British Museum. This samples is from their from one of their display. So this sample basically so the samples was excavated some years before, and the corrosions, as you know, if you have done any analysis with the corrosion product, the corrosions can be of two types. One is from the pre-excavations, which are formed during the burial process, and it reflects the environment of the burial environment. Second is the post-excavations. Basically, post-excavations when you have got your artifacts and you it get exposed to the atmosphere and or the reactions of the conservation materials, and you want to protect your material. So it's very important to get all the informations of the samples, whatever you have seen it during the excavation process. So these samples comes from a late Tang dynasty samples, early 20th century in Shandong province in China. During the excavation process, there were two types of corrosion product was observed. One is the typical green color, which is green malachite. Another one is the thin green or pale blue color phases, which is possibly linked to the environmental effects. And this was an unknown phase. So, and our goal was to identify this phase. So first powder diffraction data was performed by the scientists in the British Museum, and you can see the powder diffraction is extremely poor. There are only few peaks. There was no match with the ICD database with this powder diffraction pattern, or the other way you can tell you can almost fit everything with this quality of diffraction pattern. And then they have also matched with their in-house reference library from their corrosion products. It did not match anything else. So they also performed some same EDX, which shows some copper, presence of copper and phosphorus, and also traces amount of calcium, sulfur, and chlorine. Then later I have compared this diffraction pattern with some of the other phases, copper phases I saw got in the literatures, but I did not found any match from any of these reference phases. So then what you should do? I think then what I did, we once we got the sample, we looked it in the samples in the ACM and we saw some layer structures. So it does not make sense just to crush the sample because the sample was very small quantity. Basically, I received 2 grains as exactly as you see. This is the 2 grains I have received from our collaborator, and then we make some nice fib cut. Once we did the fib cut, that's the fib cut on the right. And we took some EDX, and once we did some EDX, what we saw, the calcium phosphorus ratio is 1:2. That's the most important thing. And we saw some strong copper signal. And that's what the informations we took it basically from the EDX analysis. And then we straight went to the electron diffractions. We pinpoint the positions, and we started rotating the crystals from -40 to 60 degree. And we got some very nice diffraction pattern, as you can see it. And once we have the diffraction pattern, first thing we did it the unit cell. And once we got the unit cell and we know the chemical information, basically it was some copper, phosphorus, and oxygen. And we matched this unit cell with the database, but we did not see anything matched with the existing database of the database. Then we solved the structure ab initio, and we got some, the structures came out quite easily once you play with a little bit with the space group. And once we got the structures, we looked with the other structures, and it has some similarities with the other minerals, which is nisonite, but there are a lot of differences. So we believe this is an unknown phase, and which was previously not documented for this type of corrosion. So the next example is coming from Greece, which is basically identifying pigments in a 5th century glass amphorisk, which was excavated in a southern part of Greece. And then the local scientists did some analysis, and then we received the samples. Basically, we have used multiple techniques here to characterize the samples, electron diffraction, CDX, and EPMA. From the EDX and EPMA, we see that the trace happens beyond silicon and oxygen, which is there always in the glass materials. We saw the presence of TiO2 and cobalt oxide and copper oxides. And then we say, okay, let's go one step ahead and see what is there more in the sample. So we did some ion thinning for the sample preparations, and once we have the sample, we went to the electron microscope, and it's very difficult to distinguish the crystals in the strong background in the amorphous phase. Everywhere there is an amorphous phase around, but we were able to identify 4 precipitates. Once we have the 4 precipitates, we collected some nice diffraction data, and we were able to get the unit cell. And once we got the unit cell, we went back to the literatures again and in the database. And from the literatures, we know there are 2 types of blue pigments are there. One is the Egyptian's blue, and another one is the millerite, osmolite type group of minerals. Since the structure is hexagonal, we discarded the Egyptian blue, and we take into account only the millerite, osmolite group of minerals. Interestingly, the same mineral was also found in Sardinia. Same mineral was found in Sardinia, which is of Egyptian origin, something like 1000 BC. I think based on this discovery, what we believe that there was a trade connection. So the same artifact was seen in Greece, Egypt, and Italy, and we believe there is some trade route existed during this period, and it is also supported by archaeological and historical evidences. So by looking simply by some phases, identifying the phases, it is possible to see some interesting informations during the technologies, during the trade route, during this period. The third example is coming from again from Greece. This case study was based on some of the Roman mosaic glasses samples. These samples was excavated in 2008 from southern Greece, and then first it was studied by our collaborator Professor Nikos Zacharias and his team by ACM and EDX to get some basic informations, and then the sample was sent it to us to do electron diffractions to study the crystal structures and its compositions. So there are 6 samples of different colors, green, blue, yellow. Here I will present only the green color one. So first the sample was prepared by FIV. So we took a 5x5 lamella, and it's a very thin sample preparation was done, something like 50 nanometer thick lamella from a very big piece. Means very big means relatively bigger piece of sample, which we have received it, and then we took out this FIV prepared lamella and we went to the electron microscope to do electron diffractions. First thing what we did it is look the sample in the STEM EDX and also in EPMA in parallel, and we see some presence of antimony, lead, and oxygen with traces of copper, iron, tin, and calciums. So you can ask me why we used both the chemical analysis technique because the EDX has a very high spatial resolutions, but EPMA gives much higher energy resolutions, because once you have so many element presence, it is good to combine different chemical analytical techniques to get a much better informations of your samples. Once we have the chemical informations, which is always crucial, then we can do something more. So one point is here, because when we were analyzing the sample, because as you saw in the EDX, we saw some copper signals, but we are not sure this copper is coming from where exactly, because in the fib lamella, which is we have prepared, there were copper. Actually, you can prepare fib lamella without copper, but we realized after the preparations that, okay, there is a copper signals, but we do not know from where this signal is coming from. It is from the lamella itself or from the support. So we did some ACM. In the ACM, we went back and we did some chemical analysis there. And we saw the 3% of presence of copper both in the matrix and in the precipitate. So that confirms actually copper is there in the sample, not in the artifacts of the measurements. Once we have all these chemical informations, basically then we did some electron diffraction studies. And we choose some crystals and we collected some diffraction data. As you can see, means usually the crystals are not well separated. There are crystals nearby, so you have to be very careful once you are collecting electron diffraction data from these samples. Once you got some diffraction data, and then we did the unit cell, which is a phase center cubic, and we solved the structures. It's something like a lead antimonate structure on average, because there are many other elements present. So basically, whatever structures we got, it's a average structures of the material. Now, the important thing is that's why the color is green actually, because lead antimonate is actually yellow. So basically, you have two assumptions. One is the cobalt, as you have seen it in the EPMA and also in the EDX, we have detected cobalt. So the cobalt may contribute to blue. Basically, cobalt is coming, means gives a blue color, and lead antimonate is a yellow color. So the mix of this can be green. The second options could be copper incorporations in the lead antimony structures like pyrochloride phases may alter its color, which is creating copper green. There are some references of this type of green color copper in the literatures. So the next sample which you have studied also is some glass material, but this is a bit of a different technique we have used it. It's called pair distribution functions, which you used to analyze the glass materials. The pair distribution function is used extensively in X-ray and neutron diffractions, and basically in simple terms, it gives informations of atomic pair distances and gives informations of the local structures. There's a lot of work on X-ray, but I believe, as far as my knowledge, there is no work has been done using electron PDF with ancient materials. But there are work in general on material science with electron diffraction PDF. So this is, according to my knowledge, the first example. So basically, in electron diffractions, in electron PDF, you get a diffraction pattern, which is Raman first materials, and you do a PDF transformations with a dedicated software, and then you get an interatomic distances, and then you try to identify your materials. So what we did exactly, these samples comes from a collaborator in Italy. And this is a sample, actually, 14th century brown translucent glass comes from Iran. And we did some EDX first, obviously. And the reason the sample was given to us to understand the color, why this brown color comes from. Is it coming from some dispersed ions, or it is coming from nanocrystalline, some micron crystalline structures? Phases is there, precipitates is there, which is giving the color, or some iron-based phases, which is well known, like magnetite, hematite, or any elements like copper, manganese, antimony is there, which is giving the brown color of this gas. But you will be surprised entirely. We also were very surprised, including the people who have given us the sample. So first thing we did an EDX. I mean, that's always we do. First, we do an EDX. So basically, we had a few preparations and we did an EDX, and exactly the compositions everywhere is exactly the same, except there were a difference in the amount of carbon in the matrix and in the precipitate. So and then, as when we see that there is no difference in terms of chemical compositions of the samples, except the amount of carbon, there is more carbon in the precipitate compared to the matrix. We collected some electron diffraction data from the matrix and also from the precipitate. And we see, obviously, it's an amorphous glass, and also from the precipitate, which is an amorphous, surprisingly. We collected some diffraction data, as you can see it here, and we did some PDF transformations from the precipitate. And then in the precipitate, we see a distance of 1.57 angstrom, which is slightly higher than the carbon-carbon bond distances. And we also did some PDF from the amorphous matrix, where we got more higher bond fast interatomic distances, which is 1.61, which is like a silicon oxide bond distances. So I have discussed with some of the people who worked in this field in the glass in the ancient materials. They told, according to their knowledge, this is the first example of a brown glass containing carbon-rich precipitates. About the origin of the color, to be honest, I don't know. I have asked. We don't know why exactly it's making the brown color, but it's a first reported glass where, which a brown glass, which has a more carbon in the precipitates. The third technique which we used is called phase and orientation mapping technique, which is commercially known as ESTAR, which is used a lot in the material science community, but not in the much of archaeological or ancient material characterizations. How it works, basically, you have a very small beam and you scan and you collect nanometer size beam, you collect diffraction data. And once you have a diffraction data from each pixels, and then you match it with the pre-calculated theoretical diffraction patterns by template matching, and then you map the phase and the orientations of your crystals. Basically, in each pixels of your collected data is color coded by its orientations with the stereographic projections. And with these methods, you can study several micron of samples to see how the phase and orientations of the crystals. But important thing is you need to know the crystallographic phase. It's not a methodology to determine unknown structures of your materials. So we have used this technique basically to study some pre-Hispanic Maya pigments, which is come from the Mayapan archaeological sites in Yucatan Peninsula in Mexico. We have received pigments of different colors, blue, green, red, and our goal is to understand the techniques and materials used in these preparations. And there are several, as you can see, we have received pigments of 3 to 4 colors, but I will focus on the red pigments here. Just briefly, once we got the sample, we made a fib cut, and once we did a fib cut, and then we scanned the sample with an 1 micron area with a very small beam, and then we got a phase map as you can see it here, and you can see it mostly have a lot of hematite as the major component in the round temple, painted niche temple, and fisherman temple. In solar temple, we see some cristobalite. But the very interesting thing is we also detected some very small amount of titanium oxide, rutile in the two places, two colors, which was not reported anywhere in the literatures, and it was not detected by X-ray technique. So then we have when we saw some unknown phases, we did some EDX map, and we saw some signals of titanium as well. And once we have it, and we did a match back with titanium oxide and did a phase map. So basically, the titanium oxide rutile is coming basically from the red soil, and the red soil means there are minerals, and in these red soils, basically titanium oxide is there, and this soil has been used to make the pigments, and that's why we see in these pigments the presence of titanium oxides. And obviously, you have seen hematite and maghemite, which is basically used for the red color. So now the last example, which is basically combining several techniques to see how important is to combine several techniques to understand a complex problem. So these samples is basically Tang dynasty come from excavations in China. It's a Tang dynasty tomb in Jian province. It's a metal headgear, and which has a to imitate gold, and the gold means to imitate gold, and that's, as you know, it symbolizes status. And we used several techniques like ACM, optical microscopy, EBST, EDX, electron diffractions, phase and orientation mapping, XRF, all possible techniques to understand how the gliding technology was developed, to understand the corrosions and in this type of materials. So first thing what we looked at is in general how the sample looks like, and if you look at visually, we can see the gliding was mostly applied to the outer surface, but it was covered with corrosions when we received the samples. And in the optical microscope, we see some globular features in the corrosions, but when you look in the SEM, it's a cluster of needle-like crystals, and that means it's very complex, the corrosions, than what it looks on the surface. Then we, as usual, first thing we did some SEM imaging, and we did some EDX. And when you look the EDX, we saw a lot of copper and oxygen present in these corrosion areas, which except there are like carbon, magnesium, aluminium, silicon, phosphorus, means any elements you can think it of. But depending, there are these elements is varying from one positions to the others in terms of quantities, but the copper and oxygen is always there in a very strong signals. And in some places where we saw some very bright region, and then we did the ADX and we saw some signal of gold, including mercury actually, and this coming from basically from the original gilded layer. Then, as a next step, we did some XRF analysis also from these samples, and we did an XRF mapping in the Albus synchrotron beamline using 50 micrometer beam to see the distributions of copper, zinc, gold, iron, and chlorine. So interestingly, gold signal was we have not seen any gold signal when we are doing the XRF. Basically, we believe the signal was obscured by the copper corrosion layers. And we have seen chlorine, as you can see in the edges specifically, where there is copper and zinc was depleted. No tin was observed because first the archaeologists told us it's a bronze, so we thought it would be tin, but we do not see any tin. And in these color-coded maps, the warmer colors indicates there is more amount of this particular element. Then we did some cross sections of the samples. Once we did some cross sections of the samples, what we see to see what does it looks like from the side, we see a very thin black layer, which is of less than 1 micron, which is basically of gold. And on top of that, there is a corrosion layer, which has a needle structures. There are two types of corrosion layers. Once we have seen the cross sections, one is like a needle-like, and there is a more continuous region. And beneath this gold layer, we see a brush. You can see some brush-like structures, which is basically 50 to 100 nanometer thick. This is one is more with copper when you did some EDX. And these are very layer structures. Basically, you see a lot of corrosions on the corrosions after you see the gold layer, and below the gold layer, there is a lot of copper materials present. And once we have seen the cross sections, then we did some FIB to understand better the structures from each part of these layers. First, we went to the corrosion layer, which is basically in the top part, and we collected some three-dimensional electron diffraction data from different regions, specifically from the needle part, which is the needle ones. And we see a malachite unit cell. Then we have solved the structures. We saw that there was a lot of disorder in the structures actually, but it was possible to solve the structures. And that confirms this phase is a malachite phase. And then we look back and did a phase and orientation mapping to see if it looks malachite only or some other phases. But actually, the top layer is the malachite, and below there is a cuprite phase, which we observed during the phase and orientation mapping. And then when we did the phase and orientation mapping, just close to the gold layer, there was another phase, which we were not able to identify exactly what phase this is. So that means there is an unknown phase is hidden in this complex corrosion material. So basically two phases identified. One is the cuprite and one is the malachite on the top. below is the cuprite, and then there is an unknown phase, So once we have some informations on the corrosion layer, we went to the basically to the gold layer, and we make some electron diffraction data. But the sample was the particles was extremely small of these particles in the gold layers, which is I think less than 40 nanometers, and we were not able to get a single crystal diffraction patterns during the tilt. So we just try, so we were not able to get any ab initio structures of these small particles. Some of the diffraction patterns we are able to index is as gold, but I believe it's the structures is much more complex than gold. It's possibly some alloy of gold, mercury, or something else, or gold. Some alloy has been forming in these layers. Once we got some, but close to the gold alloy, basically whatever was there, this is very big cuprite phases, but the gold particles was very, very small, something like 40 nanometers. Once we got some information on the gold layer, and then we said, okay, let's look the samples in much bigger scales using EBSD. Because we have seen as of now with the TM, which is scans a very small area, but EBSD in SEMs gives the informations of a very big area. And once we looked in the EBSD and we have seen it near the gilding layer, which is basically the gold layer, we have seen very large grains. What we have seen it in the EBSD, which has like 30 micron grains, which is a very random orientations, and it does not have any texture. And just below that, just the big ones, there are very thin layers of nanograins of copper, which is basically 100 to 300 nanometers, and they are not uniformly distributed even in the sample. Some places these small nano grains of coppers are there, and some places are not there. So these variations of the grain size, once I spoke with the people who works on the metallurgy, they said it gives specific informations about the thermal and the mechanical processing. So now let's summarize what does it exactly, what we believe based on the informations, what we got it from chemical analysis, from the EBSD, and from the STAR. One is basically the headdress, which is a pure copper. It was shaped by hammering. It was first made it. And then on top of that, there was a gold layer of 200 to 300 nanometers or 400 nanometers was applied by mercury amalgamations. And then once it was done, there was because of some thermal process, there was some formation of some intermetallics, not just the gold. And then during the corrosion process, first the cuprite was formed on top of the gold layer, and then the malachite was formed on top of that. But still, as you can see, the gold layer is still intact, so that the adhesions durability was very strong using the procedure they have followed to do the gilding technology. So all these results, which I have shown it here, some of them we have published, they're not all, and you can see some of the publications. So for more details, if you want to see how the sample preparation was done, how exactly all the analysis has been done stepwise, you can see more all the details of the sample preparations. So with these conclusions, I would conclude that, okay, electron diffractions is a very powerful technique. You can use it for study ancient materials in the nanoscale resolutions with a very small quantity of materials. It can identify unknown phases, even if it's a very small quantity or present, or even it's a degraded areas. But my understanding from seeing all these materials, it is always good to combine other techniques to get an understanding of the technology used, or to understand the materials or the corrosion product which is growing during in these ancient materials. With this, I would like to thank all the collaborators who has given us the samples, because when we have worked on this, studied with ancient materials, we realize getting the samples is the most difficult stuff. So I would like to thank all the collaborators from various institutions, and some of their names are here, some are not present here, for all their discussions and support, because I am a material scientist. I did the analysis. Then to understand more about the archaeology, it is always very important to discuss with the archaeologist who has given us the sample. With this, I would like to thank everyone to be virtually present to hear about our work, and I would like to thank everyone from Nanomegas for all their support and all their valuable discussions. And also, I would like to thank all our collaborators. And if you have any questions, you can always reach me by email. Also, you can reach out to me via LinkedIn. And if you see more details about Nanomegas products and all our Nanomegas applications, you can visit website www.nanomegas.com. Thank you.
Visit ICDD.com to register for upcoming webinars and to watch previous ones.